Hi guys, today's video is about a very interesting topic, the Space Shuttle versus BURAN. If you don't know what BURAN or the Space Shuttle is, don't worry, I'll go into each vehicle and all their components and capabilities for you. But do note that it was very hard to find stuff about BURAN and all its info because there's not much recorded, so the BURAN section is shorter than the Space Shuttle section. So before we get too far with the intro, let's begin with the video. The Space Shuttle is America's most launched crew vehicle, which launched on 135 missions, 133 of which were successful. But during the program, NASA lost 2 orbiter vehicles, multiple billions of dollars, and 12 crew members. So back to the question about the Space Shuttle. The shuttle is composed of 3 different large components. Each has its own function and use during the launch and re-entry sequence. They are each vital in reaching orbit or docking to the ISS or to a comet or asteroid. The first of 3 components is the external fuel tank. The external fuel tank, or EFT, is a large orange tank that is commonly associated with the Space Shuttle. That is where the propellant for the main engines are stored, but we will talk about those later. The EFT contained 2 different tanks. The tank on the bottom was for LOX, or liquid oxygen. The reason it was on the bottom is because LOX is 15 times heavier than liquid hydrogen. The tank on top was 2.6 times larger than the liquid oxygen tank, which housed liquid hydrogen. The tank is larger because the propellant is lighter, which means it's less dense, which then results in them needing more, so that's why they have a larger tank. The orange tank gets its look because there is a thick layer of thermal insulation on the tank, which is meant to keep the propellants at their super chilled temperatures. The temperature of liquid oxygen is negative 297.3 degrees Fahrenheit, and liquid hydrogen has to be chilled even colder at negative 423.17 degrees Fahrenheit. So that is why they need insulation on the tank. But the insulation also caused many problems. During the launch, the vibrations from the engines would cause the tank to lose some of its thermal protection. Then while the insulation was falling, it could damage some of the components of the launch vehicle. And at the nose of the tank is the gaseous hydrogen vent, which is to vent the excess hydrogen to keep the tanks at a stable pressure. Then lower in the tank there is a LOX vent line which keeps the liquid oxygen tank pressurized. On the side of the tank there are 2 holders for the boosters, which I'm going to talk about now. The 2 side SRBs, or solid rocket boosters, each individually created 2.8 million pounds of thrust at liftoff at sea level, increasing to 3.3 million pounds per booster as they got higher in the atmosphere. The propellant for the SRBs is not a liquid that is housed in the EFT, it is a solid propellant. The propellant contains of 69.6% of ammonium perchlorate, 16% iron oxide, and PBAN with its 12.04%, and an epoxy curing agent for 1.96%. That comes up to 99.9%. And I could not find what the other 0.1% is. And I tried looking for it for over 20 minutes, and I could still not figure out what it was. The solid rocket boosters that provided over 85% of the thrust at launch were produced in the United States by THIOKOL, which was then bought by Orbital ATK, which was then United Space Booster Incorporated, and is now currently Pratt & Whitney. That name changes a lot, and lots of other companies buying it. The SRBs had 4 segments each, and the burn time was 127 seconds. The ISP though was 242 seconds, which got them to 2.36 kilometers per second. The empty mass of the booster was 200,000 pounds, or 91 tons. The propellant mass was 1.1 million pounds, or 500 tons. The mass of a fully fueled SRB is 590 tons, or 1.3 million pounds. And all that 1.1 million pounds of fuel is burned in less than 2 minutes. Each booster is 149.16 feet tall and have a diameter of 12.17 feet. The boosters also have O-rings, which are just rubber, but they have the main O-ring and a backup, which is farther out. The purpose of the rubber rings are to insulate and protect the vehicle from the SRB exhaust. But a faulty O-ring can cause a disaster, as it did on the cold morning of January 28, 1986, as the Space Shuttle Challenger was preparing to launch. It launched, but 72 seconds after the liftoff, the O-ring gave up, and that led to a loss of the vehicle and a loss of crew. Also, at the top of each booster, there are two separation motors, which helped in the separation of the boosters during that phase of flight. Part of the Space Shuttle, the orbiter. The orbiter vehicle, or the OTV, is what most people think of when they think of the Space Shuttle. The white plane-like part of the shuttle, which houses the crew, the payload bay, and the main engines. The orbiter vehicle is part of the shuttle that landed back on the runway at either Vandenberg, AFB, or Cape Canaveral. There were 6 different orbiters made for the Space Shuttle project: Enterprise, Columbia, Challenger, Discovery, Atlantis, and Endeavour. We will go into each orbiter shortly. But first, we need to give you information about the orbiters. There were 6 total orbiter vehicles created. 5 of them went to space and came back. 1 of them was built midway through the program, and 3 lasted through the program. First, let's talk about the heat shield. The thermal protection system was one of the most complicated parts of the orbiter. The heat shield was composed of around 20,500 tiles. The reason I say around is because each orbiter vehicle varied in the amount of tiles that they had. Each tile had 4 different main components: composition, glue, coating, and the identification number. The composition of the tile is actually 90% air and 10% silica fibers, which are a few millimeters thick. If you were to touch a tile, it would feel like a plastic foam. The silica fibers were derived from a high-quality type of sand. So now let's talk about the glue. The glue was a silicone rubber type glue, which is similar to common bathtub caulking, which bonds the tile to a felt pad, which the belly of the orbiter is covered with. The felt absorbs all the pressure and g-forces of re-entry. The coating is the outer portion of the tile and is covered in black glazing, which around 95% is shedded during re-entry. And the identification number, or ID, is just so the number of the tile can be identified so they can be placed in the correct location. Now let's talk about the crew cabin. The cabin contained around 2,500 cubic feet of pressurized habitable volume, which is located in the front of the shuttle. There were 3 levels in the crew compartment. The top level was called the flight deck, then just under it was the mid deck, and right below that is the equipment bay. The flight deck is used to fly the orbiter, as it houses the seats, the control panels, and all the instruments needed for launch. The commander of the mission sits on the left side, and the pilot sits on the right side. Just behind the pilot are 2 other seats, also on the flight deck. There are 2 windows to look into the payload bay. The astronauts use those windows to help control the robotic arm, to release payloads, or grab onto something. There are also 2 windows on the top, 6 windows in the front. In the flight deck, there is a ladder where you can climb down to reach the mid-deck. The mid-deck is where the crew eats, sleeps, and do their science experiments on orbit. They have lockers to store valuable items, or just supplies for the astronauts. Then next to the lockers on the right, there are 3 bed stations for astronauts to sleep in. Then the rest of the astronauts sleep in bags, which are also located on the mid-deck. And then on the left of the lockers, there is a galley. A galley is used to prepare food for the astronauts while they are in space. Then on the other side of the ladder, there is a bathroom. But for NASA, it's called the waste collection system, as it's more complicated than a normal bathroom. Then, right next to the bathroom, there is an airlock, which is for when the astronauts need to perform an EVA, or extravehicular activity. They put on their suits, enter the airlock, close the airlock, then open the other side, so they don't release all the pressure from the shuttle. There are also 3 seats which are able to be set up on the mid-deck and 4 on the flight deck, so that is 7 astronauts total. And just below the mid-deck is the equipment bay. That is what holds the waste management systems, water tanks, pumps, and extra storage if needed. Now let's talk about the orbiter. The orbiter vehicle has 5 engines, 3 of which are used during the launch, and 2 of which are used to correct the trajectory in orbit. There are 3 SSMEs, or Space Shuttle main engines. The main engine is the RS-25 engine. The nozzle ratio is 69:1, which is just between a sea level and a vacuum engine. As the RS-25s burn all the way to orbit, the propellant that the RS-25 engines burn is the fuel in the external fuel tank. Remember that liquid hydrogen and liquid oxygen? That is what the engine runs on. Under the orbiter, there is a connection point where liquid oxygen is sent through. Then just to the side of that, there is another point, but instead of liquid oxygen, liquid hydrogen is sent through it. The manufacturer of the RS-25 is Rocketdyne, Pratt and Whitney Rocketdyne, and Aerojet Rocketdyne. Its predecessor was the HG-3 engine, which was made for the Apollo era. I'm not going to go too deep in how the engine works, but if you want a video on it, just ask me in the comments, and I will probably make a video on how different types of rocket engines work. As you can see, the engine is very complicated, and they do compress this into a smaller area so that it is more mass efficient. At the base, which is more visible, you have the nozzle. The nozzle controls the flow rate of the propellant and where it goes. So at the top left, you can see the hydrogen inlet. The hydrogen then follows the tubes down to the high pressure fuel turbo pump, which is then pushed into the main combustion chamber. And while that's happening with the hydrogen, it's also happening with the liquid oxygen. And while the fuels are being pumped, the fuel is also being mixed into the pre-burner injector that lights a fire, which then spreads to the main combustion chamber that causes the propellants to light, and then that creates thrust. And the excess propellant that is unburned goes through a hot gas manifold and then re-enters the low pressure fuel turbo pump. That then goes through the cycle again, but while all of that is happening, the hydrogen turbo pump is pushing some hydrogen through the main fuel valve, and since the hydrogen is at cryogenic temperatures, they use the hydrogen to cool down the nozzle, as they have pipes running along the nozzle for the hydrogen. But that is it for the RS-25 engine, so let's get to the other pair of engines. The OMS thrusters are in the shuttle by the aft section, still by the main RS-25 engines. There are 2 OMS thrusters which are just modified AJ10-190 engines. In the engine, there is nitrogen tetroxide, nitrogen, and helium. And there are also many other vents, which is to release the pressure buildup, but aside from that, that should be it for the orbiter vehicle. Now let's talk about staging on the shuttle. Let's start at T-1 minute. The crew is already in the launch vehicle, propellant load is completed a few hours ago, and the nose cone cap is retracting. T-minus 30 seconds to launch, the sound suppression system begins to dump 1.3 million pounds of water on the pad. At 11 seconds, the rofies ignite to burn the excess hydrogen. Then at 6.6 seconds, the main RS-25 engines begin to start. At T-minus 1.2 seconds, the boosters begin to start, and at T0, the shuttle lifts off from the pad. After 1 minute 12 seconds after liftoff, the vehicle passes through max Q, or maximum aerodynamic pressure, and around the same time, the shuttle goes supersonic, or faster than the speed of sound. And then at 132 seconds after liftoff, or 2 minutes 12 seconds, the boosters are jettisoned. And the vehicle climbs through abort zones. But after 8 minutes of climbing, the RS-25 engine is cut off, and they're in a parking orbit. Then after a few minutes, the OMS thrusters begin to perform as the shuttle gets into orbit. And that's all the info about the American space shuttle, but now let's talk about Russia's version. here onto BURAN. I honestly had no idea of anything what it was before recording this video, so it took multiple days of research to figure out what BURAN did and all of its components. And this video section is still pretty short because there's not that much info on it, but let's start. BURAN is actually the shuttle name. The rocket's name is Energia. The Energia rocket was a super heavy lift launch vehicle which was developed by the NPO in the USSR or Soviet Union. It contained of 2 stages. It stood at 192 feet and 9.6 inches tall, and its diameter was 57 feet and 10.8 inches. Its payload to LEO or low Earth orbit was 100,000 kilograms or 220,000 pounds. Its core stage contained the same propellant as the space shuttle, liquid hydrogen and liquid oxygen, except unlike the space shuttle, there were 4 main engines on the bottom of the fuel tank. The core stage would burn for 480 to 500 seconds with its 4 RD-0120 engines. Then it also had 4 side boosters, but instead of solid fuel, they also used liquid fuel. But instead of hydrogen, they used kerosene, which is also known as RP1. So the mix of RP1 and liquid oxygen for the side boosters, they would each burn for 156 seconds, and they were each powered by a single RD-170 engine. Now let's talk about the RD-0120 engine, which is on the center core. On the left of the image, you can see both the liquid oxygen and the liquid hydrogen inlets. Then below are low pressure turbopumps. It spins the propellant into the main turbopump. Now for the turbopump to work, you need the propellant to already be spinning the engine. But they have a solution. They have a little pyrotechnic charge in the engine, and it spins it just enough so the propellant can begin to spin through the turbopump, and then that allows the engine to start. And then after that, it spins through the main combustion chamber, and then it creates thrust from the bottom of the RD-0120 engine. So now that we have knowledge about the RD-0120 engine, or the center core engine, let's talk about the side boosters engines. The RD-170 engine, on the left side, on the left green pipe, that is the kerosene inlet, and the blue on the right is the liquid oxygen inlet. The kerosene gets fed into a fuel pump as the liquid oxygen is fed into a LOX pump. The hydrogen is then directly pumped into the main combustion chamber of each engine, but the liquid oxygen is sent to the main turbo pump and fed off to each engine. That is why there is a large flash prior to engine start due to the kerosene exiting the nozzle after being ignited by the preburner, but not mixed with the liquid oxygen. And since it isn't mixed with the liquid oxygen, there is no thrust being produced by the engine. However, it should be known that the RD-170 is the most powerful engine ever made. But don't you think the Saturn V's F1 engine was? Yes, but that was the most powerful single combustion chamber engine. The RD-170 has 4 combustion chambers, which help to create more thrust. Except the RD-170 was derived from the RD-150, which was just 6 RD-151 engines combined together. But the RD-151 was very troublesome, so now let's get into learning about the RD-151. So in the graph, yellow is for the fuel, which is kerosene, and the aqua blue is for the oxidizer, liquid oxygen. So now let's inspect the graph. The kerosene gets pumped in through the fuel pump, which then flows through the nozzle to create a cooling system, like the space shuttle's RS-25 engines. And the kerosene gets injected into the mixing head, where the liquid oxygen is flowing straight to. Then they combust in the combustion chamber, and then you have an engine. Except it really didn't go that well, as there are reports of the test going wrong due to combustion instability, where the engine exploded and debris flew almost 3 kilometers away. But what is combustion instability? Well, it is where the thrust of the plume of the rocket doesn't stick to the walls of the combustion chamber or nozzle as it should. That causes the nozzle to bend and flex in ways you shouldn't want it to, and that can lead to a red or rapid unscheduled disassembly. You can see some combustion instability on the space shuttle's main RS-25 engines when they are still sitting on the pad, but that wasn't catastrophic as the engines were designed to do that. Now let's talk about Energia/BURAN'S staging system. At T-4 seconds, the side boosters would ignite. At T-3 seconds, the center RD-0120 engine would start, and at T0, the clamps would release and Energia would have liftoff.
Energia getiriyor.
16 seconds after liftoff, the engine began to pitch the vehicle over so that it could enter orbit, as orbit is not just being in space, but continuously falling around the planet. And for Earth, you have to be traveling at around 8 kilometers per second or 27,000 kilometers per hour. Then at around 2 minutes into flight, the boosters would cut off and jettison, and the core would burn for another 5 minutes or so before they are in orbit. Once they are in orbit, BURAN separates from the core and fires its OMS motors to get into a full orbit. After they orbit the Earth and their mission is complete, they begin to deorbit the BURAN. So they start their deorbit burn, which slows them down 0.45%, but that's just enough so that they can re-enter and land. So once the re-entry starts, it will last around 6 minutes and create a communications blackout for around 4 minutes. Then after the shuttle begins to fly around to the site to land, at 400 meters, the landing gear will deploy, and at 0 meters, it will touch down. First of all, NASA's space shuttle had a large external fuel tank. BURAN also had an external fuel tank. NASA's shuttle had boosters, so now the Soviets want boosters on theirs. But for Energia, their boosters were liquid-fueled instead of being solid-fueled. That makes them a lot more safe and reliable as they are able to be shut down. As NASA's SRBs wouldn't be able to shut down until they ran out of fuel, they also had an orbiter vehicle, so the USSR added BURAN. The space shuttle was in service for over 35 years for the United States, and BURAN was in service for less than a year. The space shuttle managed to launch 135 missions in 35 years, and Energia/BURAN launched a single mission, and it was fully successful. NASA lost 2 of their 135 missions, which brings them to 133 of 135 missions that are a success. So that's a 98.52% reliability rate. But since BURAN only had 1 flight, which was a success, and BURAN has a 100% success record. Also, BURAN is able to fly without crew. The American space shuttle needs at least 2 crew members to be on board to operate the vehicle. But NASA's space shuttle wasn't more reliable as it had had 133 successful flights, with BURAN only having 1. And who knows, BURAN's other flights could have completely failed. They may have just gotten lucky the first time, but we will never know. But BURAN's design is a very smart move, replacing the solid rocket boosters with liquid-fueled boosters instead, as it makes the vehicle a lot more safe. But that's it for this video. It was very fun making it, and I hope you learned some new things in this video. Also, if you would like me to make a very long video on how different types of rocket engines work, please comment down below that you would like to see it. But thanks for watching, and I'll see you in the next video.